Okay, so is it recording? You are sharing and recording? Okay, sounds good. Okay, so hello everyone. So I'm happy that you got assigned to the World-Class Quantum Chemistry Challenge with TKET. So who am I? So I am Catherine Spendier. I am a quantum technology evangelist from Quantinuum. Give a little bit of background. I was a full tenure track professor. I received tenure at the University of Colorado Springs, running a biophysics lab with doing super resolution microscopy. Besides that, I was teaching pretty much every undergrad and graduate physics course you can imagine you're exposed to at a university setting. So I recently joined Quantinuum as a quantum evangelist for the whole purpose of getting people introduced into quantum computing and help them find their path. And I am focusing here on TKET. And some of you may be wondering what TKET is and how it falls into this challenge. I will talk about that in just a bit. But the first thing I want to say is, if I can go to the next slide, is that I don't know if you've heard it, but we just at Quantinuum had a big breakthrough where we have shown for the first time that logical qubits start outperforming physical qubits. So this is a very big step. We just announced in Quantinuum. So if you want to go and look up to it, there's like the article, which is in the archives. But pretty much by doing this, being able to show that we have now logical qubits that outperform physical qubits, we can do error corrections, right? And that is all the holy grail, one of many of them in quantum computing. So we did that with our trapped ion device, which is just super exciting. And go check it out, the details for it. Okay, so what about the challenge? So pretty much the idea of the challenge at the application side is that you have fossil fuel powered vehicles nowadays, right? And they cause a lot of pollution. And what we are doing as researchers, we're trying to come up, and inventors coming up with new solutions of how can we avoid this pollution nightmare. And the different ways, like you have electric cars, right? Or in this case, for example, you have a vehicle powered by hydrogen fuel. And in this case, you know, it's kind of like a little bit of magic, not really magic, there's no magic, but it's really amazing. You put in hydrogen and you get out water vapor as your exhaust. It sounds really good, right? But obviously there are challenges. If you look at the car, you have to have the battery, or in this case, the hydrogen tank on the car. Right now, what you have is you have compressed hydrogen gas on the car in the tank. And obviously you can't compress that much gas. So what this industry is looking for making a material that is not gas, but rather it is a solid material. And there is where lithium hydride comes into play. So lithium hydride in a chemical reaction can actually like produce hydrogen. So the goal here is you can find a lot of papers out there. The goal here is that you come up with a way of storing that lithium hydride, right, with other players in the mix, right, so they can produce hydrogen for your hydrogen vehicle, right? So that's the idea here. And again, you can go outside, research this topic quite a bit, and you should be able to find the details in different industries that look into it, and different labs that look into this. But the idea is that you are kind of helping develop this way of solid hydrogen storage. And can it be done? And the idea here is that it is a very difficult calculation to do on a chemistry basis. And the idea is that you could apply quantum computing in order to model the chemistry of this solid hydrogen storage materials. Okay, and please do raise your hand if you have a question. Okay, let's go to the next slide. So what is it all about? You see my slide with the circuit? You see my circuit slide now? Yeah, okay, good. So what is it all about? So this is just an example circuit of H2, right? So this is a chemistry-inspired circuit of H2. It has 150 gates. It has 80 layers. It has over 50 C0 gates, right? So what the challenge is about is you have these complicated chemical systems. You can develop a Hamiltonian for it, you can go on, right? But then eventually you're going to have a circuit. And this circuit is going to have to be implemented on the back end. And the problem here you are having is that you come up with a circuit, right? And you're like, oh, great, I came up with a circuit. The algorithm may work, but this is all happening on a computer. You haven't really put it onto the back end. And that's a very big problem right now. It could be almost a deal breaker if you're not able to put this 4-qubit circuit onto the back end, right? If you can't route it or route it onto the back end. And on top of it, it is very long, right? This is for H2. It's not even for lithium hydride. So you are tasked to come up with a circuit for lithium hydride eventually. I give you a sample circuit, but that's not ideal for that backend, because the sample circuit I'm giving you for lithium hydride is 12-qubit circuit. And that's really hard to run on current machines. So what you need to do, I want to show here, you have the initialization, and then you have a lot of gates. You can see some patterns here. But the whole point here is that you are trying to optimize the circuit, right? Make it smaller. And then you try to route it onto the back end. And when you route it on the back end, I hope you have learned that each back end has specific basic gates that are unique to the system, right? So you may have heard that when you went through what you have done so far. So what is it all about? So this specific circuit we want to optimize, and we want to route to a back end. So what is it all about? So here you may have seen this. So here you have the 21-qubit IonQ area. This is the layout of the qubits. So each qubit can talk to each other, for example. It's a fully connected circuit, qubit map. We call it a routing map or topography map. Then you have the Lucy one, right, which looks like this. OQC Lucy, it's like an 8-qubit circuit. Then the 7-qubit IBM circuit, the Oslo one. You can see that qubit 3 talks to 1 and 5. And qubit 0 only talks to qubit 1. This is the Washington one. Here you have the 20-qubit Quantinuum circuit. It is fully connected. Every qubit can talk to each qubit. And anyways, you can go through this list, and then I want to pay your attention. Here you have the basic gates, right? So for the Lucy, you have the RC, CX, SX, X, and ECR gate, for example. For Quantinuum, you have the unitary 1Q, which can do any rotation, the RC and the CC gate. So in any case, you can see how complex that is, right? So in essence, you have to route your circuit, you come up with your analysis onto your background, and you have to make sure that it's going to be, you can be able to run it. Obviously, you can't be an expert in all these backends, which is definitely a challenge, right? So it turns out now that TKET is a way for you, it's a tool you can use for this specific challenge to take the circuits you have, right, and route them to different backends and figure out which backend is the most efficient, right? Which backend will be able to implement that circuits theoretically if you do analysis. And if you get a hands of the backends, you could run on them, right? So maybe you want to see how you can bring in qubit into this challenge. I have not worked with qubit. This is something they have told us like very shortly. And I have not worked with qubit, but in principle, you can upload all the PyTicket because TKET is running through PyTicket, and we'll talk about it now in a little bit. Upload into the qubit, and then you could maybe use their hardware to access all the backends. But I don't know if that's going to work, because then I was able to try it out. But pretty much, TKET is an open source software platform, and it's specifically developed to execute gate-level quantum computation, right? So it doesn't do annealers, and it doesn't do photonic devices right now. So keep that in mind. What I want to say, it's there for optimizing circuits and for a wide range of hardware. And it uses this module called PyTicket. Okay, that's PyTicket is the model we're going to upload. And pretty much you can use Qiskit to code, you can use Cirq to code, any coding language you can use. Then you have a few little lines. You can go convert to a ticket, so PyTicket circuit. Then you can run the PyTicket software on it, right? The optimization and routing protocols of PyTicket, and then you can send it to different hardware backends. So TKET stands in between all the languages you can use and all the backends you can use. It's kind of like a glue in between, more or less. And this is something TKET is very good at. So for example, for this challenge, I know Qiskit has chemistry, right? Their nature package out there with a lot of chemistry tools. You can use that. You can use Qiskit documentation. You can use Qiskit tools, right, to do it. But you can optimize the circuits using TKET. Does that make sense? So to optimize the circuits, you want to use TKET for different backends to make sure that you have, for example, not meant, it shouldn't be deep, right? The circuit shouldn't be deep because you add noise and noise and noise. And you don't want to have many multi-gates, right? 2 qubits gates. You want to minimize that number, right? So you want to route it. So that's the idea of like minimizing it. You need a compiler that can handle all of your different backends and can handle the front ends if you wanted to. Use different tools and packages. Okay, so here I just want to show you, and I like obviously going to make these slides available, but there is benchmarking out there by the Arlene compiler benchmarking paper. So Arlene has done benchmarking without us being involved, without Qiskit being involved, without BiCX being involved, without Circ being involved. They have come up with a benchmarking paper, which you should be reading. And pretty much in this benchmarking paper, they have looked at different compilers, right, what they can do. So here, for example, for quantum chemistry, specific compilation steps, there's a compiler called BiCX-PI. At this paper, at the time it was published, I think the version of TKET was actually from 2020, so it was an outdated version of BiTKET. But in any case, you can see how a benchmarking can help you make a decision of what compiler you want to use, right? So BiTKET in essence has done really well. But for example, if you use Circ or Qiskit, you might not be able to optimize the circuit as much as you can. So you want to add to it. What is really nice too for this challenge is that Arlene has shown that, for example, if you use some of the compilers in a given arrangement, you may have a better optimization, right? So the goal of this is that you are able to actually optimize the circuit, come up with a circuit, a way of developing something for answering the question, can you make a material, right, that can store hydrogen? If you can do this, what chemical would be useful? I said lithium hydride for a start. You could do something else if you come up with it. You can try to find a chemistry inspired circuit for the specific computation, right? And then you want to compile it and route it to a backend, to a most efficient backend, right, for your specific application. So this is the goal. Not just doing the hard work of coming up with a circuit, right? There's another part of it actually getting it implemented. Because if you come up with a nice circuit and a nice thing to run on a quantum computer, if the quantum computer can't do X NOT gates and you have them all over the place, then it's bad, right? So you have to figure out how to fix that problem. So in any case, so this is this here. So for example, totalization, which is something very important to do, PiTKET was really good, right? So it was like a very good optimizer for this specific problem. So anyways, this is kind of like in the NISQ area, right? This is kind of like a very important thing to do. You have to work with the noise in the quantum computer. You have to understand the noise. You have to understand the qubit coupling maps. And this is all pre-programmed, right, for you to use, but you have to decide which tools you want to use, right? And TKET is one of them, the tools that have proven to do very well in many different areas. But again, it is your choice to choose the best compiler or the best symbiosis of compilers to make it work. That makes sense, hopefully. Okay, so this comes now to the challenge, right? So obviously you're all at different levels, which is totally fine. And what I suggest for you to first to get started is to get a feel for TKET, right? How does compilation works for TKET, right? You can use this in different quantum circuits. You can play with calling different, for example, you want to know how many gates do you have? How deep is the circuit? how many specific gate types do you have, right? So I would ask you to like get used to that. You can use your own circuit to start, right, and see how it works, or you can use the lithium hydride circuit I already prepared with this 12 qubit. It will be very intensive on your machine when you try to compile this big 12 qubit circuit with like thousands of gates. It will take long on your machine to compile, right? And depending on what kind of machine you have, it may take longer than you want to. So I would suggest to you to like start with your own circuit, a small circuit you would like to use to get your hands on it and understand the compiling part, right? And once you feel comfortable with the compiling part, right, and even with its test circuits, you maybe want to try out some backends, right, already. So I would go through this, that you start with getting to know what compilers do, how they root, and play around with the compilers out there. TKET is obviously the one I think is a really good choice because you're doing well in a lot of different areas, but you might find a compiler that is better than TKET for a specific application. Get used to that, right? And start with chemistry inspired circuits, which I can provide to you. And then once you feel good with that part and you have figured out how to access different backends, because that's the thing you have to figure out too. How can I access different backends? How can I run on different backends, right? Then I would suggest to you, because it's the core part of this challenge, to make it work. And then you go to the chemistry inspired part, where you then try to push the problem. Right now I know how it works, and now I can come up with different circuits. I can use the Qiskit libraries, right? The tutorials for chemistry to go through it and come up with my own material I would like to analysis. And then you can do the VQE algorithm. You can do the ground state energies, for example, excited state energies. And that would be now very interesting if you go there and ask a question. So, well, I came up with this backend, it seems to work well, but there's another backend that was really good, right? What is if I apply the same circuit to this backend, I route it, right? What result would I get? Is there any difference, right? Is the difference between the different backends to get your result? How does it compare to something which is published in literature? So this is kind of like the ideas you should think about. What happens when I add noise, right? So error mitigation, right? Can I, add something there? Like, would it be better? So for those who are very like, you have already understand something with chemistry and you have maybe seen it before, which I know we have different levels of where you stand in your studies in quantum computing, right? So anyways, there's something for everyone, I hope. For those who are interested in this initial problem of chemistry inspired circuits, how can you route them? How can you run them on different backends? And then for those of you who really want to go and push that field forward by using quantum computing to find a material. And I see I have 2 questions here in the chat. Sorry, I didn't see that before. A couple of quick reminders. Oh, is that the chat to everyone? Oh, I see. Okay, yes. So I will, the chemistry inspired circuits, I will definitely send to you. So that comes to the next thing I want to show you. So this is a GitHub page, which I have been working on, and I haven't really released it yet to the Womanium one, but you can all access it. And I will probably put this in the chat if I can, without doing something. I will put it in the chat in just a little bit. But this is the GitHub notebook I made for this challenge. And it pretty much goes over getting started with PyTicket, right? Building circuits with PyTicket. How do you go from PyTicket to Qiskit or PyTicket to Cirq, for example, if you have a different language you prefer? How do you get access to Quantinuum IonQ backends through Azure? These are all free accounts you can set up. And how you get access to IonQ, Rigetti, and OQC via AWS bracket. And obviously IBM backend, do you all have an IBM Q account through this Womanium? Yeah, so you already have the access to some of the IBM Q products, right? So anyways, in principle, you can get free access to all of these. And because we're using the simulators, right? So did people tell you about the difference between simulators and the actual hardware? Did you hear anything about that difference? So simulators or emulators, more or less simulator emulators supposed to like simulate the noise level of the backend, right? In the actual backend, then you run it, which takes some time. There are queues. But for this specific challenge, you should be able to just use the simulators, which are pretty much accessed for free in order to route and maximize your circuit. So what to say that to? At what level of theory basis set is the current implementation of ground state calculation? Is it a single harmonic oscillator most potential? Okay, so this is a good question. Pretty much this is Jordan-Wigner, very similar like Hamiltonian basis sets I'm giving, but you can pretty much, it just works with the typical potentials. You have electrons and nucleus, right, which to feel in that area, but you can more or less go and explore that part totally on yourself, by yourself, okay? Ashley, I hope I answered your question. Okay, so now what I want to do is I want to open up the GitHub repository. And for this, and please, if you want to just unmute and talk, I'm totally okay with that. If you have questions, I wanted to discuss something while I'm getting ready here for the next step.
I guess, are there any important like equations, or other than the VQE algorithm is pretty important, but just for the lithium hydride kind of any equations that we should know?
So lithium hydride is actually something, I'll give you a hint there, something IBM has pretty much explored quite a bit. And you can find a paper by IBM on lithium hydride, for example. And it goes through the chemistry, it goes through bond lengths, it goes through the whole paper. I think the paper was done, obviously a few years ago, right? Because it was kind of the first circuits they implemented, but you should be able to find quantum computing stuff on lithium hydride through IBM, for example. So there has been works out there in literature that can help guide. Good question. Other questions? No? Okay, so I show you that link, and I'm gonna put that into the, make sure that you, so I will try to have the first README part of the GitHub account. So right now I'm hoping, oh no, me too, Ashley. So now the direct message, sorry. I want to message to everyone. Everyone in the meeting. Okay, so did you get the GitHub link? Look at the chat. Open it up, bookmark it. I will try to get it onto the Quantinuum, the Womanium hackathon page, right? The GitHub page. So now I want to go over that. Oh, that's cool, yes. Okay, so let's go here, and I'm gonna share my screen again. Okay, so do you see now the GitHub page I'm sharing with you? Yeah. Okay, so pretty much this on your outline here. I just letting you know I'm mostly like available during this time of the day, but I won't be available August 11th to August 14th. That's very important. I'm on travel and I'm on mountain time. And weekends, obviously, I won't be very responsive. It could be by luck that I look at my Discord, for example, but else, please understand that weekends I will be not as available as during the week. Then there's something else I want to show you, and maybe we should increase the size here, the font size, is that obviously we're also going to have a TKET. You can access the TKET development team, right? People who are experts in the TKET pieces through the Slack, which you can join here, right? Slack channel. or you can email to TKET support with the question. But I suggest that you join the Slack channel and they will get back to you. Pretty much what I would do is first reach out to me, okay? If I feel like I don't have the technical understanding of TKET specifically for this, for your question, I will let you know to go out for Slack and get the development team of TKET, if that makes sense. Okay, so that's the first thing to do. Then pretty much this is a notebook. I have uploaded different Jupyter notebooks for getting started with PyTicket, building circuits with PyTicket, going between Qiskit and PyTicket, how to run on the back end, IBM, and all this. So these are all notebooks I developed, right? What you probably know, in order to run it on your environment, you're gonna need a token, right? In order to API token you put into your system. Again, you can use qubit. You should be able to, for example, getting ready with PyTicket. If you look at this notebook, right, for example, you can use, instead of setting up your own environment, if you're not comfortable with this or you don't have a Jupyter notebook already, which I would be using, right, Jupyter notebook, you can just open up qubit, your environment of Womanium, and just do pip install PyTicket and type in pip install PyTicket Qiskit, for example. You should be doing that, and then your environment, even in qubit, should work, right? So, but again, I haven't worked with qubit, so any kind of questions for qubit platform, please send it to their development team. There's some other useful readings about TKET, qubit routing, phase gadgets. You can look here, look it up here. Then, building circuits. Again, you can look all at these. We also have examples for TKET to run on different backends and circuit optimization and advanced techniques, right? And then I go through here over the beginner side when you start getting used to compilers. So I have a Quasum code, right? And the Quasum code, which is this chemistry inspired one, these Quasum codes here actually are not chemistry inspired, sorry. The list of Quasum codes here is from another Quantinuum Hackathon, but you can download these Quasum codes. I go through one of the notebooks, how to open a Quasum code. This is Open Quasum, but they're like different codes you can use for testing the compiler. And at the bottom of this file, if you go all the way down, there's the circuit log CV, which tells you about how deep that circuit is, how many qubits it has. So you can actually look at, so if you click on this, hopefully it opens up. Yeah, so for example, these circuits here, it says what type it is, how many CC gates you have, and so on, right? So it tells a little bit about the circuit. How many qubits, right? So maybe at the beginning you don't want to start with like a 12 qubit circuit. They're really heavy, right, for your machine to use. Maybe you want to start with like a 2 or 3 or 4 qubit circuit if you don't want to come up with your own. Okay, and here's the challenge again. The Jordan-Wigner LIH circuit is in this repository. So you're going back to the Womanium Hackathon ticket challenge. And right here, you see I have actually 2. This is the H2 Jordan-Wigner, right? That's the one I had in my presentation, which is the 150 gates. And then here you have the LIH Jordan-Wigner, which is a 12 qubit code circuit, sorry. This is a 4 qubit circuit and this is a 12 qubit circuit, okay? So you can use them to also play. So these are the chemistry inspired ones for your challenge. Okay, and this is just outline of like how you can approach this this challenge, letting you know the LIH circuit, which is chemistry inspired, has 16,000 gates, right? It's huge. So that gives you like an idea what you actually deal with when you try to implement these things on a quantum computer, right? 16,000 gates, it's a lot. How much can you optimize it to, right? Could you optimize it to something useful for a quantum computer? When 16,000 gates gonna have so much error that you can't run it, right? What are the optimizers now capable of doing? And I hope that you are realizing how important that part is in quantum computing, optimization and routing to actually get these quantum circuits to work. And then I also have here a link to your Nature documentation, right, for Qiskit, because they're doing a really good job for the LIH molecule. And then you can explore. You really can explore a lot in this challenge. If you find something besides LIH, you could model another chemistry-inspired material, right, for hydrogen storage. Go ahead. If you come up with a different, better material, do it. Don't stop there. You can really push yourself if you want to. This is the Arlene benchmark I told you about, right? This is the paper. If you click on it, a paper will open. Oh, that's actually that's their GitHub repository. But you want to look observation here in the paper. And it's going to be an archive paper, which you can open. It's freely accessible. And it goes through how benchmarking works, right? And it will tell you about the different tools. But I want to caution you. TKET's version for this specific analysis was September 2020. Qiskit was February 2022. CX, which did really well too, was June 2020. And CIRC was 2021, right? So obviously, in the last 2 years, different compiler SDKs, right? SDKs have developed new things, right? And so on. So I just, as a note of caution, is a good guidance, right? But you may have to do your own little bit of, your own investigation. But in any case, I'm hoping that this is a really good starting point. If you have something where you feel like I cannot code this is not clear, especially with the TKET, right? Some more ideas of like coding it, let me know. And if this is something that the whole group here could be of interest, right? I will try to make a notebook and stick it right onto this, hackathon manual for TKET. This is why I wanted to keep it away from the Womanium GitHub, because I want to have full control over what I can post on this. I heard someone saying something. No? But anyways, I guess that would be it so far. Do you have we want to brainstorm something? So how many teams do I have actually here right now? I'm curious. Do we have some team speakers or something? No? So you all have like 6 on a team? You can unmute yourself right now and talk if you want to.
I think mine is 4.
Yours is 4?
I didn't communicate with anyone. I filled out the Google form, and I was assigned to a team of 4 people, I think. And I see some of the names here, but I didn't meet anyone.
Okay, so one thing you have to do now is to go out and coordinate with your team, right? How would you start this? It's a big feat. How would you start it? Do you have thought about how you would organize your team to get started?
I mean, first of all, we need to communicate, I guess.
Yeah.
I'm planning on finding them on Discord, I think. If I cannot, I'll just email the Womanium team so they can match us with those emails. And then maybe some Microsoft Teams or Slack or something like that. And then we can get started.
Okay, great. So, divide and conquer. That's what I want to tell you with your team members. Divide and conquer, right? Have paper, maybe look at different things to get started and then report back, and figure out what you want to do. I think there's going to be a lot of brainstorming going on. Yeah, Rena, go ahead.
Hi, Catherine.
Hi.
So my team has 5 members. It's called Qpolis, and it's me, Dustin, and some other guys that I don't see at the moment. But I wanted to ask you 2 technical questions. Yesterday, I was trying to understand the things that we had put on GitHub, the link that you just posted a few minutes ago. So I started yesterday exploring it, and most of the steps worked fine, but I got stuck at this step, access to Quantinuum and IonQ. So the idea was to work with Microsoft Azure. I don't know if I pronounce it correctly. Azure backend. And at this point, I'm a bit confused if we will have to work on Qiskit, on Anaconda, or we should go to the Azure website.
Okay, so that's a good question. Keep going. If there's something else you want to add.
Yes. And at this point, I received at least 2 errors. One of the errors was on my notebooks on Jupyter. I tried to install Q# following all the lines, but I received this error. Partially initialized Q# has no attribute noise model. I don't know if you have seen this kind of error before. So I switched to Azure portal, and I thought, okay, let's run all the circuits on the Azure portal, but I couldn't do that either because, for example, it said cannot import render circuit Jupyter from pitcat.circuit.display. So
Okay.
I encountered errors both on Jupyter notebook and on Azure portal.
Okay, so that sounds like definitely something we can look into. So if you want to hold on and show me your notebooks later, is that something you want to do?
Yes, I can do that.
Okay, great. So it's thank you, Rena, for hanging on here. And let's see if I have other questions. Miriam, if I pronounced it correctly. Oh, no, no more. So are there any questions? Any further questions? No? You good? Okay, so happy hacking. Good luck with everything. Rena, please stay on. And I can look at the notebook. I will stop the recording here. So we can look at what your problems are. Rena, sounds good?
Yeah.
Yeah. Okay. And for everyone else, you're happy to leave and we can look into the problems. Okay. So stop recording. It's nice meeting you all.
Nice to meet you too.